All right, thank you everyone. So I'll be talking about Tracy. I'll short give you an introduction to what the project is, why we did it, show some potential use cases, then I'll go to the background, how does it work, present some features, some implementation details and future work, and if we have some time I'll present some more of the work we already did in the future work. All right, so the main motivation is that we want to trace system calls on different architectures and different platforms, so that would mean Linux, BSD, etc., as well as on Intel architectures, ARM architectures, etc. This is kind of hard. I mean, that would be nice. This is fine. All right, so
that would be better.
Thank you. All right, so there is this system call called ptrace, and it's implemented in BSD and Linux and most of the UNIX systems, but it's not very cross-platform in the sense that the API differs on all platforms and architectures, which is kind of to be expected, I guess. All right, so we provide system call tracing, and you can hook into system calls and signals, but you can also modify system calls, which is a very useful feature, and you can even inject system calls. Use cases for this could be jailing processes, so you can attach to a process with ptrace, trace all the system calls it's doing, and modify them so it won't access certain files or write certain files, etc. You can do transparent routing of I/O, which we implemented, and we can probably show this later. You can also do debugging, replaying I/O or whatever. You can do some fault injection by modifying the return codes of the system calls to say, hey, we're actually out of memory and you can't allocate more memory. And you can do I/O logging. All right, so I went a bit over the top there just now with just using the term system call. I'll briefly explain it. A system call is just a fundamental interface between the application and the kernel and the hardware to which the kernel interfaces to. So that way you can interact with the hardware using your program. Examples would be, well, very typical examples: open, write, socket, fork, wait. So we did use the ptrace system call in Tracy, which is, well, pretty much the only way to do it efficiently. But we provide an abstract layer that would work on other platforms and architectures as well. So how does it work? Basically, with ptrace, you either start a process and the process says, well, please trace whatever I'm doing, or you can attach to an existing process. And then you can either tell ptrace to trap on every instruction. So every instruction executed by the program will send you a signal and the process will be stopped, and then you can do whatever you want and resume it. Or you can tell it to only trap on system calls and signals, which is what we're doing because the other case is very slow and we don't need to do it. It's also noteworthy that ptrace isn't actually POSIX, although you might think that the P is for POSIX, it's actually not. And, well, as I said, it's no uniform API. So like I said, obviously our library is event-based, so you can tell the library to, well, tell me something when, say, getPit is used and call this function, and then you can execute whatever you want in that function. The same goes for signals. Well, this is an example of hooking into the read system call and then calling this function. You can inject system calls when a process is suspended. I'll talk about this in the implementation later. And you can quickly read and write to memory. Well, quickly most of the time, depending on what your kernel implements. We have support for both the Intel architectures and AMD architectures and ARM. And we have some bindings for Python, although we wrote everything in C, so you can also use it from C, obviously. All right, so how do we implement system call injection? This is kind of the main core of our work, aside from just well, you know, tracing system calls is easy. So what we did is, when the program performs system call, it is stopped, and then we can do whatever we want. We can change the registers, we can change the instruction pointer, we can change the stack pointer, whatever. frame pointer, sorry. And so what we do is all the system call arguments are in the registers, so we can change them. We change the system call number, and then a different system call is executed with different arguments. And once the system call is done, we reset the instruction pointer to the previous instruction, which was again system call, and restore the registers to what they were before. So you don't actually modify the program aside from whatever effects of the system call has. We also distinguish between synchronous and asynchronous injection. So you can either say, hey, I want to inject the system call and wait until it completes. Or you can say, hey, inject the system call and then call this function when you're done, which is nicer if you have an event-based program. So there are different ways of accessing the memory when you're tracing a process. You can do this using the ptrace system call, but for every word you have to call the ptrace system call, which is very expensive. Where you can use the special mem file in the proc file system, which is relatively fast and which is what we're using, but you need a somewhat recent kernel for this to actually write to it as well. And as of a very recent kernel, there's also these two system calls which allow you to do the same thing. Okay, so this is what we did so far, and we did some more work, but this was the basic thing I wanted to talk about. So what we want to work on is memory sharing between the Tracy and the tracer. So the Tracy is the program you're tracing, and you are the tracer. Use cases for this are if you say you want a jail process, and the process is executing an open call with some path, and you want to check the path and see if it's valid, then another thread in the process is not actually suspended, so it might change the string as soon as you said, well, this is an OK string, go right ahead and open the file. So what you should do is copy the string to some safe memory location, which is allocated in the process, otherwise it can't read it from a system call, and then make sure that no threads can write to it, and then you can safely execute the open system call. Another big issue is, and this is also why we didn't support BSD yet, but we're planning to, but we didn't do it yet, is that when a process forks on Linux, you can set some special flag which will immediately make Linux trace your that process as well, but it doesn't work on BSD. So we made a solution for this and we tested it on Linux, but not yet on BSD, but it should work technically. Speed is a problem, especially when you're doing a lot of system calls. Handling one system call requires 4 context switches. So that's quite painful. You have to, like the process to be switched out, you will do something, and then you can resume the process, and then you will be in charge again once the system call completes. So it's kind of painful, and it can become really slow, especially when you're tracing something like Firefox. And an open resource question is how cross-platform we can actually get, because Linux does a lot of funky things, like using different system calls for basic stuff like networking on 32-bit that's different than 64-bit. So yeah, that's kind of a problem we didn't solve yet. How many minutes do I have left, approximately? I guess a few minutes. All right, so I guess I covered this. This is just a solution to verifying, say, the argument of open and make sure it isn't changed by some thread. All right, so this is more interesting. When you're running a, like I said, the fork system call, a new child is created and it isn't traced automatically on BSD. So you need to execute the fork system call or clone or whatever system call creates a process in a safe environment of which it cannot escape, so you can then attach to the process and thus trace it. So what we did is we eject some assembly in the process we're tracing and then change the instruction pointer to run that assembly, and the assembly will basically execute a fork call, send a new PID, so you can attach to the process, and then just do nothing until you attach to the new process and just modify the instruction pointer to move away from this endless loop. Finally, like I said, the speed is an issue at times, and I wrote a small kernel patch which would allow you to tell or to make ptrace notify you only of certain system calls, or when a system call doesn't match a certain set of system calls, so whitelist or blacklist. And that really improves speed if you just want to say only trace, read, and write. It's not completely stable yet, and I did it in about 2 days, but it does work. So that's it. This is me, and these are the 2 other students I did with at the University of Amsterdam. Thank you for your attention. If you have any questions, then shoot. Hang on, he's coming with the...
Why the microphone, please?
So, how is this different from ptrace or other tools that came before?
All right, so ptrace is a tool we use, but ptrace is architecture dependent. So, like reading memory is different on architectures. On BSD, you can read memory fast, but you can't trace processes. System call numbers are different on architectures, and usually when you look at programs that do like use ptrace on several platforms, they have a separate platform file for like that's their ptrace stuff. So if you have a more specific question. Other questions? Sorry?
The microphone is coming, so we will be able to hear your question. Here you are.
Thank you. I was wondering whether you will upstream the patches for the ptrace syscall selection. That would be interesting to me personally.
Right. Well, there are several main problems with that, and that is this has been tried before, this kind of patches, and it was rejected because it wasn't complete. And now there's something, I think it's called secure computing, seccomp, in the kernel, which does something similar but doesn't allow you to unset which system calls you want to trace, which is kind of a pain. I mean, for jail it would work, but in general it's not complete yet. So this was more of a proof of concept, which I wrote at the time, and I might look at see if I can get it to mainline, but it will probably be very hard. So if we're like 30 seconds, I could probably show a demo. Well, never mind, it works.
Yeah, we have time for a quick demo.
Okay. So what I will show you is a program we made which will trace all the socket calls and reroute, it will connect to a proxy server rather than the actual server, set up the SOX5 protocol, and then just send over all the bytes. So you can transparently route all the network traffic on the TCP at this moment of a program. I made a very small video, so I hope it's visible, but we'll see. Right, so we'll just run the program twice. Once with our, first we'll just run curl, which will return us some IP, and then we'll run it with our transparent networking thing. And you can see the IPs are different. It's a very simple proof of concept, but it works also on Firefox and other programs. Thank you.